Okay, let's get started. If first of all, if I remember correctly, the deadline for assignment number 1 is this Sunday, right? Okay, yeah, make sure you submit your first assignment, otherwise you lost marks, and the marks are sort of easy things that you can earn from these assignments. So last week we spent quite some time to talk about the method of slices, and we had one rather comprehensive examples that walked you through how to use the simplified method to evaluate or to get the factor of safety of a slope, even it is not a circular one, okay, even arbitrary um, slip surface. And indeed, in real life, this is the factor of safety that you obtain is just for that particular slice. So what you need to do is to try many slices so that you could find the so-called critical slips, which give you the minimum factor of safety. And this is the factor of safety for that particular slopes. And of course, if the factor of safety is below certain threshold value, certain designed value, you may need to upgrade the slopes. And that's why today we're going to talk about a very common method in Hong Kong to upgrade a slope, which is the use of saw nails. And I believe that you have heard about saw nails many times, and in lectures or by reading some engineering articles, attending public seminars, you should have heard about these terminologies quite often. And today it won't be, I try to strike a balance between a very in-depth discussions of saw nail and as compared to a very superficial discussions. And I'll try to stop or find a way that balance the calculation part and the construction part and highlight, I believe, at your level, at this level, as a final year graduates, what you should learn, those basic ideas. We won't be able to have design examples to go through because I think it's a little bit heavy at this stage. And indeed, the design example is, I would say, the design of saw nails when you practice as a geotechnical engineer. Probably your company will have some standard worksheets to do the calculations, but they won't tell you the mechanisms behind. They won't tell you the theory behind. So I think here at university, I would rather spend time highlight the philosophy of the design. So let's see. First of all, we talk about some backgrounds of saw nails. And you see that, well, I only got a few bullet points because it only highlight the key stages of using saw nails in Hong Kong. Now, first of all, saw nail was not first developed in Hong Kong. It was developed in the early 60s, 1960s, okay, for the use of, I would say, stabilizing something, especially when we are constructing tunnel. So they use it to as a stabilization measures to stabilize the tunnel face. Okay, and when I say so, not tunnel face, but the uh, tunnel body. Okay, and in the early days, it's pretty straightforward. So people simply think that, okay, I just install some steel bars into the ground and then I just shotcrete the face. And this is the very early days saw nails. If you want to make a comparison, it's just like what? It's just like you nail some, you put some nails inside a body, okay, to join something together. And if you don't put a nail, that will sort of fall off. So that's the early days saw nails. And then in the 80s, the soil nailing technique was introduced to Hong Kong, and we start to use it. And the reasons behind is, you may ask, well, in the old days, we still have slope problems, right? We still have a very steep slope. So what are we going to do in the old days without the use of soil nails? There are a number of measures that we could do. As I discussed earlier, maybe you build retaining wall. Maybe you further cut back your slopes to make it more gentle. Or in some cases, we install what we call the pre-stressed ground anchor. Pre-stressed ground anchor was once very popular. Okay, so if you may consider like just a nail, similar to a saw nail, but it was pre-stressed. There is one big problem of using pre-stressed ground anchor is we don't know, because the entire stability depends on that pre-stress forces. And the question is, when we first install the nails, we know the amount of pre-stresses. That's what we design. And we know that based on this design force, the slope is safe, okay, or reach a certain factor of safety. With time, because of the nail will creep, that means it elongate a little bit, which means your stress level may drop. So if the stress level drop to a certain extent from the calculations point of view, you may not have sufficient force to stabilize the slope from a force equilibrium perspective. And in order to tackle this problem, we need regular monitoring. We need regular revisiting of the pre-stress anchor. What we need, for example, what we could do is to go back to those nails, go back to those anchors, and check the pre-stress level. If the pre-stress level becomes lower than a certain threshold, which means you're not satisfying with that stress level, you have to pre-stress it again. All right. So what does it mean? Additional cost, additional time. Okay, you have to go back and you have to maintain. You have to, if it doesn't work, you have to increase the stress level again, and it is very costly. The reason behind is if your nail, if your pre-stress anchor is going to stay there for 50 years, you monitor 50 years. If it's going to stay there for 100 years, you monitor 100 years. So it's not a good way to do. And in many cases, don't think that monitoring or pre-stressing a stress anchor is easy or simple. It's on the slope. So you can't simply send a worker and bring all the tools and go there and check. You have to build, for example, some temporary access, temporary working platform, safety measures. There are lots of things, site supervisions, many things, okay? So the cost itself could be huge. So people were trying to explore, instead of using pre-stress anchor, pre-stress it, can we use something similar without any pre-stressing? So we just install the nail there, no pre-stressing. Okay. So the saw nailing technique become popular since the 1990s, and we have more and more nails installed in Hong Kong. One of the reasons is later on we have more design guideline on the use of saw nails, and people know how to use it, how to design it. And an important driving factor is, in many cases, it is cheaper. Cheaper than what? Cheaper than building retaining wall, cheaper than many other ground improvement, whatever options. So it's not expensive. And the disturbance to the environment in many cases is smaller than having huge constructions of retaining wall. So that's, I would say, in most of the cases in Hong Kong, it is, saw nailing is the preferred options. Okay, Now, this is an important point, because when in Hong Kong, when we do slope upgrading works, you only design one options. You have to present several design options to your client. And then you evaluate each option. For example, the cost, for example, the construction time, for example, the environmental impact. You have to consider a basket of factors. And in many cases, after considering that baskets of factors, we choose soil nails. Okay. So nowadays, well, it's extremely common to use soil nails as a slope upgrading or stabilization method. And the last bullet point somehow just give you a rough idea how many slopes or retaining wall has been upgraded using soil nails. Okay, we could also use soil nails to upgrade a retaining wall, because if your sliding of the retaining wall is or does not meet the factor of safety, that means your wall, because of your lateral earth pressure, is too high, that may try to push your wall forward. We could use soil nails, okay, as a measure to stabilize it. So what does it mean? It means something like this. So if I have retaining wall, let's say I have a retaining wall like this. Okay, let's say this is a retaining wall, and for some reasons the factor of safety is not adequate, especially in terms of sliding. What does it mean? That it means that the base frictions or the passive pressures here is not sufficient to withstand the active pressures, right? This is what we call sliding, okay? When we consider horizontal forces equilibrium with a sufficient factor of safety. So if that's the case, we may consider, okay, we build nails to strengthen the systems, so that you have additional, when you push it, the nail will try to have the frictions try to hold the wall, right, in the lateral directions. So this is how we use soil nails to stabilize a retaining wall. Okay. There are certain, I call it basic elements or basic ingredients of a soil nail systems. And from the name itself, it's very clear that you must got nails, right? So the nail is actually a reinforcement. And of course, in many cases, it's a steel reinforcement. So we call the soil nail reinforcement. And of course, in Hong Kong, we mainly use steel bar. And now we have some more environmental friendly materials instead of steel. But it's beyond the scope, and I don't want to mention the names to complicate the issues. But you know that apart from steel bar, we have other options. Okay? And as long as that materials could take tensile, could provide tensile resistance, it's okay. That's the working mechanisms. Of course, you may also consider corrosion. You may also consider some other factors these days. For example, carbon emissions during the productions of the materials. And that's the main reasons why people consider to use non-steel material. They don't want to use steel anymore these days because of carbon emissions. Because during the productions of steel bar, we got huge carbon emissions. And now people are considering using some fiber glasses, okay, or fiber reinforced polymer, because these kind of new materials produce less carbon during the productions. So tensile resistance, okay, keep that in mind. We'll come back to this later. And then we need to have reinforcement connector, and people always miss this point, connector. Why? if you got saw nails of 15 meter, okay, for example, based on your design, you need a nail of 15 meter in length. You cannot find, or even you cannot ship a 15-meter long nails from the factories all the way to the construction site. Even you could bring it to the construction site, the construction worker cannot handle a 15-meter long bar. So in practice, it may come with 8 meter, 12 meter or so in the length that it can be handled, and we use coupler to connect those pieces. So we need coupler. Okay. And when we say coupler, if you still remember, a couple of years ago, we have big news in Hong Kong, which is about the problems of couplers in the Hong Kong stations, MTR stations, right? Coupler, for example, the connections here, or the use of coupler here, was not doing in a proper way. Okay, so you could introduce some other problems, but this is something that we cannot avoid because you can't actually have that long nail in terms of constructability. And another key element is the grout along what we call the sleeve. Okay, and this is straightforward because you drill a hole, you put your reinforcements into the hole. There's no connections, there's no coupling between your reinforcement and the ground and the soil. So we have to fill the hole with grout, and the grout will provide bonding between the soil and your reinforcement bar. Okay, so it helps to transfer stresses between the ground and your reinforcements. This is the first functions of the grout. There's another functions that people may forget is as a corrosion protections. Okay, we want to seal the bar, just like what? Just like concrete. We consider concrete cover. We use the concrete materials to protect your steel reinforcement from corrosions. Okay, same thing. Apart from having the grout as a protection measure, galvanizing is one typical treatment for the steel, which help to reduce the degree of corrosions or try to avoid corrosions. And we could also provide some plastic polymer things to protect your coupler. Head. When we after we install the nail, after we grout the whole thing, the entire system is not yet finished. We will construct a head. Okay. The idea of having this head is to provide reactions here, because your nail will try to push it or pull it. So the head will try to provide, for example, this is a ground surface. If I have an exposed head, my nail will push it like this, and then, or it depends on action reactions. So you got reactions here. Okay. You provide the head, we try to spread the load here. Okay. So that's the head. And this is the practice in Hong Kong that all nails should have a saw nail head. This is not the design practice in some other countries. For example, if I remember correctly, in Japan, you can have nails without the head. So they simply consider the nail itself could will be sufficient to develop the tensile force and then to stabilize the slopes. And later on, I'll talk about why they think in that way. But in Hong Kong, we still use saw nail head. There's another good thing of having saw nail head. If you look at the slope surface, for example, this is a slope. If you look at it from the front view, I have nails installed into the screen. So I will have saw nail head, saw nail head, saw nail head, something like this, right? Saw nail head, stacker like that. It should be square, sorry, but I didn't in a good way. Okay. So once you have all these head, it actually helps to work as a surface protections of the slope to reduce the chances of having erosions, surface erosions. Of course, in Hong Kong, you may vegetate it. You may have some grass to vegetate. You provide mesh. You provide lots of surface protection thing. But the nail itself, the head, sorry, the nail head itself work as a surface protections against what? Against when you have heavy rain, your rainwater will hit on the surface directly and then you erode the soil. So you must provide something to protect the surface. So this comes to the last part, slope facing. So if we provide vegetated cover with some erosion control mat, we call it the soft facing. On the other hand, if you spread concrete, if you put a lot of guillage system, guillage means you have a lot of beams here, concrete beams, or even in this vertical direction. So you have a lot of concrete beams on the surface. It also helps as a surface erosion control. Okay. All right. So soft cover, hard cover. And of course, from the layman's perspective, I may enjoy soft cover more. It's green, right? It's promote vegetations, carbon, blah, blah, blah thing. But from a practical perspective, if you got a vegetated surface, in many cases, you have more work to do to maintain it. And probably hard facing will be much easier. We do have guidelines in Hong Kong. If I can't remember exactly the degree, but maybe 60 or something. If your slope angle is lower than 60, I'm not too sure about the number, but if your slope gradient is smaller than a certain threshold, you must do soft covering. Okay, you must do vegetations. Okay. Of course, you may ask for exception provided you have good reasons, but in many cases, there's no good reasons behind, and you have to do that. So we talk a lot about saw nails. We said that, oh, nowadays in Hong Kong, we use it often, saw nails. There must be some good things about saw nails, or we call demerits. So here, I extract some key merits that I extract from the Geo Guide number 7. And I think it's easy to be understood, and probably I just highlight a few points. For example, it's easy, relatively easy from the construction perspective. You don't need to have heavy machine. And I sometimes joke with my friend because to construct saw nails, probably you only need 2-3 workers to do. And indeed, that's the reason why many workers, they just form a small group and we call Pun Tao. So they will do the work. They will get the job from the main contractor and then they do it by themselves. Okay, so that's a very typical ways in Hong Kong. So that group of worker will have their own machine will have their own human resources, and they could set up a company to do by themselves. And I sometimes joke with my friends saying that, okay, we should establish something like that, and then we simply get a few workers and then we establish a company to do. So the equipment itself is not too heavy and it's not too sort of large scale, and you could easily handle it, which is good for slopes, because if you got very heavy machinery, very big size machinery, how could you put it on slopes and work, right? You may argue saying that, okay, I construct some temporary platform. That's expensive. So if your machinery is simple, light, it's good for sloping works. And environmental things I've mentioned about that, normally speaking, is less environmental impact as compared to constructing a retaining wall. You need lots of concrete, reinforcement bar, and formwork, force work, lots of things. Okay. And in cutting back, you excavate a lot of soil, you have to find somewhere to put it. So this is, in many cases, we think soil nailing would be a better options from environmental perspective. And of course, another issue is tree. For example, if you got a slopes, again, I look it from the front face. This is a slope. So I think you know what I'm talking about. This is a crest. And this is the toe. And in many cases, you got trees, right? So you got lots of trees. Many could be. If I look it from the elevations, it may be something like this. Okay, you got lots of trees. Right? If you do retaining wall, let's say, well, for example, I put a retaining wall here. Okay, I have to fell lots of trees. And it's not that straightforward in Hong Kong to fell a tree. You have to do get lots of approval to do that. Okay. But by having saw nails, you may say, oh, I only have saw nail here, there. Okay. If based on the design, I need to have a nail here, and it somehow clash with the locations of the tree, I could reallocate it, right? Put it to the left or to the right and do some calculations in this specific area to demonstrate that, okay, now the distance become a little bit larger than what I expect in the original calculation. So this nail must be a little bit longer, something like that. So you can still tackle it using calculations. And it gives you high flexibility when you come to the site in which you have a lot of trees. And in many cases, you will only know the exact locations of the tree when you move to the construction stage. Okay. During the design stage, you may not know exactly, or you even do not want to spend time to understand the exact locations of the trees. Okay. We do ask the the designer to map all the trees, right? But my experience is that when you come to the site, you may find, oh, some location is wrong, and we have to do a lot of on-site modification things. Nail would be flexible in that aspect. Okay, you could slightly adjust the locations. And well, I think the rest you could read it yourself. But there are still limitations. And some limitations are not only for saw nails, it actually affect no matter schemes you do. For example, there are utilities or underground structures, okay, maybe pipes, water pipes, maybe telecom services, okay, cables, that, well, as an obstructions to the constructions of nails and even to other options, retaining wall. So in that case, maybe you have to do some more work. Maybe if you use saw nail, you try to rearrange, reallocate the nails locations, or maybe you first have to discuss with the utility companies to redirect those surfaces. Okay. And another thing is now let me see. I use this page to sketch it because I got more space here. Okay. If this is the slope, okay, and the stability is not good, one option is to cut back, for example, make it more gentle, right? And of maybe, oh, this is not an option because later on I'm going to have a buildings here. I want to have a buildings here. So I can't cut it back. So we think, okay, let's install saw nails. Right. What could be a potential problem of using saw nail in this case? What could be a problem? You plan to build buildings here. Maybe your building needs to rest on piles, right? If you install nails here, you can't build your pile foundations at the back. Okay, so you're not allowed to do that because then you can't actually adopt the piling options. So this is another limitations of saw nails because it would take up some spaces behind the slopes, and you may need that space. This is one example. Another example is this example is you have the nails and then it somehow stopped you from constructing piles. Another example is I got a buildings, existing buildings. I got piles already. Okay. Now I come and check this slope. Well, the safety margin is not good, so I need to upgrade it. I cannot upgrade by having nails. Even my calculations show that it's not going to touch, it's not going to clash on the piles. But then the owner of the building say that this is my lot boundary. I own this piece of land. Your nail cannot enter into my boundary. I don't allow you to do that. So this gives another limitations of nails because again, as I mentioned, it take up some space of the ground and you're not allowed to do that. Okay. Even not building, I told you another examples that when you graduate, as I mentioned many lectures ago, highly likely you'll be working on some Northern Metropolis projects. Northern Metropolis, one very unique thing is you got lots of graves because of those villages. Okay, these graves are normally on hillside, feng shui feng shui issues, right? So you got lots of graves scattering around the hillside. And maybe you need to construct a road. Say, oh, you got a hillside here, and you got lots of graves here. Okay. For example, one typical sections. And now government say that, okay, I need to construct a road here at this particular level. So you construct a road here. So you got a car, okay, going into the paper directions. So you have to cut the slopes. right? In order to give space for you to create the roll. So you may say, oh, I do some slope cuts like this. And factor of safety is not okay. I install nails. Sorry, I own this space. Even there's nothing here, I own this space. You are not allowed, again, you are not allowed to have your nails put under the graves. Okay. So, especially nowadays, especially in Hong Kong, very congested urban setting, very congested setting, not only urban, but very congested setting, even in the rural area. These are limitations that impose on saw nails. Okay. Even we understand that saw nails is a good solution. And then you may argue, you may ask, what should we do here? We cannot have the nails, right? Because the villagers say they claim this land. What options could we have? What could we do? We definitely cannot have this very steep slope cut, right? Because the factor of safety is not sufficient. But we must have a road here. What other options we could have? Anything? Anything that you could think of? I need to, I definitely need to cut this saw away. Right? One option is to, I think you learned the cantilever wall, right? So you put cantilever, sorry, it should be a straight line. So one option is to construct cantilever wall. So the slope remains something like this, and then you free the entire space here. Okay, I use different color. So you free entire space here, right? Because you have the retaining wall. But this option is usually expensive because you have to actually key into the ground for sufficient length. Otherwise, you will not have sufficient cantilever arm to make it stable because your pipe pile or whatever cantilever wall is still subject to large lateral pressures. You need this, where's my nose? You need this part to provide the resistance, right? Earth pressure to provide resistance. Okay, so these are some practical issues that we may encounter when we use saw nails. There are some other things. For example, water. If you got an active water aquifer behind, you drill the hole, water just keep coming out from the slopes, right? If you got a lot of water in the slope, how could you grout it? No way you could grout it, right? Because waters keep coming out. Right, so there are some other points, but I think you could, well, read it by yourself. Here maybe this point. Let me talk a little bit more about this point. Okay, what does it mean? If the ground can see what they call high contents of fine, and to me, it's not simply high contents of fine, but high contents of clay materials. What happens to those materials is cripping, long-term movement of the clay. So you may argue, so what? Think about a nail like this. Think about a nail like this. So I got nails here. Okay. If the soil creep, that means the slope will move. If the slope move, it will, because the nail will try to hold the slope. Slope move means that it will mobilize the nails, right? So that mobilizations of nail is not due to, for example, groundwater change, rainfall, this kind of slope stability problem. It's actually simply due to the creep of the material. And in many cases, this is not the design philosophy, because design is used to hold the slope against this kind of failure, but not the expansion of the slope material itself. Okay? So it will induce additional loading on your nail, and maybe we haven't designed it for. So that's another limitation. You have to consider that. It doesn't mean that you cannot use it. It doesn't mean that you cannot use saw nails, right? But you have to take that into consideration. And in some cases, to handle this problem is the approval body will ask you to monitor your nails or to monitor slope movement for maybe 1 year, 2 years. And the data demonstrate that the amount of creeping is so small that is somehow negligible, for example. Then they will say, oh, that is okay. Okay. So they allowed you to do this. They allowed you to design saw nail on that, but you need to provide monitoring. That's cost, right? Nobody wants. Hey. So how it works comes to some mechanical considerations, physics, how it works. If the soil moves, okay, move in a way like slope instability, so there's a failure plane like that, you can easily imagine or visualize that there will be a zone of soil that try to detach from the back. We call this the passive zone. So the area of soil or the zone of soil in which doesn't have any movement, stable. And the zone of soil that actually move or slides or whatever you call is what we call the active zone. So there are movements or relative movements, and this relative movement will generate the frictions along the nails. And these frictions along the nails will transfer to the tensile force of your nail. Okay, so let me repeat. First of all is the friction along the nails. And then these frictions, of course, including the reactions here, the frictions will then mobilize the tensile force, the tension of the nails. And this is still imaginable, right? Later on, I have a better figure to illustrate what happened. So we go back to think like just a nail that we use to connect two parts together. It works like that. This part, or here you got frictions here. This part is trying to provide sufficient anchorage or anchorage force such that the whole thing will be pulled by this anchorage force. So you somehow stop this sliding. Okay. So active, passive, I have mentioned before. So we use the passive zone, which provide the forces to stabilize the whole thing. Keep that in mind. Later on, I'll show you how the forces look like along the pile, and then you will better visualize what I was talking about. But here at this stage, the key information is there's two zones, active and passive. Passive is at the back. Passive, no movement, okay, or small movement. Active is something that moves. Okay. This is the figures that I was talking about. There are frictions. Okay. So the friction develop along the nail, which means the friction will, from free body diagram, will be transmitted along the nail in a way like tensile force. So if you dive deeper, if I got an axial force at this point, which is smaller, and then you along this nail, you have a lot of frictions trying to pull the nail from my left to my right. That means at this point, you have very large tensile force. Okay, as simple as that. So we transfer the forces from frictions, from movement to frictions to tensile. Now, based on that, even we didn't come to any equation yet, based on this sort of interactions, you may already know what we need to check, right? Think about that. If we got this kind of free body diagram or load transfer mechanisms, one thing we definitely need to check is whether your nail or your steel bar mechanically is strong enough to take that tension. Very straightforward, right? If the tensile capacity of your nail is so small that cannot help to take this axial force, what happened? It break. So from the basic mechanisms, we know that later on when we do saw nail design, this must be one of the mechanisms that we have to check, the breakage of the nail. And other mechanisms will be frictions. Okay. We also need to consider that if the frictions here is provided by, this is the steel bar, and then you have the grout here, right? You have the grout. If the grout and steel interface, the bond at the interface is too weak, you cannot have the frictions. I think that is very smooth, right? You don't have any actually bonding between the grout and your steel bar. No frictions can be developed. So the whole thing cannot be used. And that's why another thing is we have to check if the bond here is large enough to support the frictions. This is another thing. Okay, at least from the first principles, we understand that we need to check these two ingredients. And apart from these mechanisms, if we make it a little bit more complicated, because the soil, because you also have the nail, you also have some overburden acting, okay, acting well in the form of confining stress. So it's very clear to have this green arrow, the soil bearing stresses acting on it, and because it may bend. So at the same time, you may consider there must be some shear forces, must be some bending moment along the nail itself. Okay. But since a nail is a rather strong materials, normally we don't need to consider bending effect and shear force effects because they are very small. We do not expect the nails to bend a lot. We shouldn't expect something like this. The nail should be used primarily based on its axial forces, the tensile force. This is what we or how we make the nail very effective. We don't want to align the nail and make it bends a lot. So orientations of the nail, because we want the nails to take tensile forces, but not bending forces. So we have to arrange the nails in a way that it should be something like, or in terms of slipping plane like that, the nail should be sub-horizontal. Sub-horizontal means is close to a horizontal line. This is how the nail will perform best. When I say perform best, is these orientations will facilitate the nail to develop tensile force. We want the nail to develop tensile force. On the other hand, if this is slope, if the nail is construct something like this, very subvertical, then we got something like this to happen. And if that happens, the nail will not be mobilized, or the tensile force cannot be mobilized along the nails. It instead mobilizes the compression force, which is something that we don't want. Okay. Any questions up to this point? So we say sub-horizontal inclination is preferable. Anyone knows in Hong Kong practice what will be a typical angle? What would be a typical angle making between your nails and a virtual horizontal plane? 10, 20 degrees. Okay. And this is the angle that the contractor also favor. Why? Think about you drill a hole into the ground. If you drill in certain small angle, it will be much easier to drill a vertical hole like that, because you need to provide lots of reactions here to drill a vertical hole. So they don't like to drill holes which is very subvertical, and they prefer something subhorizontal. And this is good, because this is exactly what we want, subhorizontal. Okay. Then I need to spend a little bit more time on this. I got a nail like this. I got a failure plane. The failure plane somehow divided the nail into two parts. You still remember, right? At the back, we call this passive. At the front, active. This is a slip plane. Okay. So let me do again, because I see a lot of question marks on your head. This is a nail. This is somewhere the potential slip plane will cut through the nails. Behind that slip plane, this is the passive zone. In front of the slip plane, the active zone. And you can imagine that the nail will try to make use of the frictions here to stabilize it. And when you work with the directions of forces, you expect, or we will expect, the tensile force along the nail like this. Along the nail, it will increase, because I see more and more tension develop along this nail. Okay, if I do it here, this is a nail. This is the end of the nail, and at the very end of the nail, the tensile force must be 0 because there's no end bearing forces here. So this is 0. And along the nail, we have this friction developed. So at certain point along the nail, we see tension developed, right? Increase because I have more and more frictions develop along it. Then when we touch that potential failure plane, the tensile force becomes smaller and smaller. Why? Because your frictions will change directions, right? You try to, tonight you go back home, take a chopsticks. Okay, you think about, okay, you pulling a chopsticks one end, so at the very end you develop frictions and then you increase your tension, right? So there would be a point that there will be a point in which your tensile force along the nail will be maximum. This is the maximum force that will be developed along the nail. And we have to make sure that this tensile force is smaller than the capacity of the nail itself, the tensile capacity of the nail. Otherwise, it breaks. Okay. Any questions? Any questions? All right. No worries. We'll come back to this slightly later when we consider the force equilibrium things. You have a better idea what I was talking about. Let's take a break, and then we come back to talk about failure mode, which is not complicated at all. When you understand, if you understand what I was talking about, okay, this failure mode should not be something that surprise you. Okay, let's take a 7 minutes break. We come back at 7:40. Okay, 7:40. Okay, let's resume. So we have spent quite lots of time to understand the mechanisms, okay, to understand how the nails work. And let's get back to something from an engineering perspective. So what we need to check eventually when we do the design, what borders us? So here, first of all, as you could recall in many other geotechnical subjects, for example, retaining wall, for example, slope problem, we always consider modes of failure, geotechnical modes of failure in this case. And when you look at the names, well, it's basically what we learned in our retaining structures. The reasons behind is we consider the nail system work like a rigid block. So if you try to analog it with your retaining structures, the whole thing here, the reinforced area, could be considered as a gravity wall, for example. So we don't bother whether any internal members, any internal plane of this rigid body will failure, because this is a rigid body, it's no failure at all. And we check the whole thing as a rigid one, and then we consider, for example, overall slope stability. So we got a failure planes here, failure slip, and maybe another failure slip, and maybe another failure slips like this. And then you check whether it failed or not. Now, this part of the nail may mislead a little bit, because you may say, whoa, you got some areas here, so it's not rigid body. So here you could actually forget this one. So suppose this block is a rigid body, and then we check against this sliding. Okay. Sliding failure is another common mode, so the whole thing works like a rigid wall. So you have pressure pushing here, you have frictions, and then you consider whether this friction is sufficient to hold that lateral pressure, active pressure basically, with a sufficient factor of safety. And bearing capacity failure, same thing. The whole thing work like a block, and then whether you have this failure thing, right? Bearing capacity failure. So not much different from a retaining or gravity wall. Okay. This is what we call the external failure mode, or in many cases, I call it the geotechnical failure mode. How about internal? Internal here means we consider the structural part in many cases, the structural element, failure of the structural element. And that's why you see a lot of checking on, for example, breakage of the nail, pull out of the nail, so the frictions, the bonding is not sufficient to hold the nail, so it breaks. Bending, shear failure of the steel by itself. Even I mentioned that in many cases this is not governing. So in the calculations in Hong Kong, we skip this part because we know it's not governing, okay, in terms of internal failure. And in terms of some local failure, for example, erosion, bearing failure, and there's some unreinforced area, again, normally we don't check. The reasons behind is the practice in Hong Kong. For example, nail distance, the spacing, we do have some guideline. For example, horizontal spacing, normally smaller than 2 meters, horizontal. Vertical spacing, normally 1.5 meter, 2 meter, okay? Which means you should not have a very big gap between the nails. Apart from that, we always have, for example, shotcrete as hard surface, or vegetations, or wire mesh as a cover as a protection. So again, we don't actually use any equations to check this point. Bearing capacity failure. In many cases, we do not need to do separate calculation to check, because for typical nail size, typical forces of the nail, we know this is sufficient. So we don't, again, check it because we know that will be okay. Unless you use some very uncommon nail head size, which we don't, we won't use that. And some other thing will be the structural connection things. So for example, you got a head, you got the nail, and then if you look at a little bit more details, I think I have the figures here. This is how it looked like. You got a nail. You got a nail here. You got the reinforcements, steel bar. And you got a saw head here. We have a little bit structural detailing here. So you have the reinforcement thing, you have nut, you have plate to form a systems here. This kind of system, you can see typical details, which means in Hong Kong practice, you don't need to do calculations. You simply follow the standard drawings. And then the contractor will follow the standard details to do the constructions. Because we check the standard details, we know that will be sufficient to stop or to prevent failure, like, okay, the connection here fell, or something like this connection fail thing. We know by following those details, it's okay, it's safe. Okay, so we don't do design at saw nail head. Structural design, I mean, detailing things. We have standard drawings to follow. Okay. Based on what I have mentioned, so probably everything come back to maybe two things. First, breakage, that we may need some calculations. Second, interface problem, friction problem, whether the friction is sufficient. Okay, so later on, I'll show you equations, how these two can be checked. Okay? Because all other things based on the standard practice in Hong Kong should not happen. So all these calculation checking have been waived. Okay, so I'll talk more about design, even though we are not going to have any particular examples to do. I was once thinking to use some company examples. I mean the design job that we have at AECOM, and of course I will erase the name, erase everything, and then just show you the calculation thing. But I think that's probably too much, and I don't want to disclose any AECOM thing, so I skip that one. I will simply tell you the procedures. This three-step approach is not something that I invented myself. It was actually copied from the Geoguide 7 for slope saw nail design. And indeed, the philosophy here, the approach here, not only apply to slope problem, but apply to all geotechnical problems. First of all, we need to build a geological model. There are many names that you may find it very confusing or looks very close with each other. Geological model and ground model look very similar, but they are different. Okay, they are different. They're not the same thing. So let me talk about what do you mean by geological model. From the name itself, geological, geology. So it must be something related to ground layering. It must be something related to water table, water flow, sort of things. Okay, so this is what we involve: geology, geomorphology, hydrogeology, basically geological features. Okay, how thick is your fill? How thick is your colluvium? How thick is your decomposed granite? How thick is your highly decomposed granite? Where is your rock head? Something like that. Okay. And some of the informations we could actually deduce from GI. You drill a hole, you collect samples, or not really collect sample. You drill a hole, you log your soil core, so you know from which depth to which depth you have colluvium, which depth to which depth you have um, um, completely decomposed granite, for example. And the flow of water will be something a little bit more difficult. You may install piezometer, which give you the water pressures. Okay, but you only have piezometer at certain locations, and you only have those monitoring data during a certain period. In some cases, you are asked or you are required to monitor the groundwater pressures over at least one wet season or at least 1 year, because that gives you sufficient information to do the design, to understand how water flow in your slope. But it doesn't mean that you can always capture the worst scenario. And you only have a few points of measurements, or I mean locations. In some cases, especially in very complicated cases, you have to get geology involved, because geologists may have a better understanding on how actually water flow in that regions. Maybe there's a valley, maybe there was some underground aquifer. So in complicated case, you may consult them. This is the first model, geological model. Okay. With the geological model alone, we cannot do the design, because in many cases, those geological models are too complicated. Maybe from your log, you see, oh, 1 meter of grade 5, and then another half meter of grade 4, and then and come back to 2 meters of grade 5, and then 1 meter of grade 4, like sandwiches. And then you may you may occasionally hit some boulder, and then go back to soil. So the log could give you very comprehensive information that in many cases too comprehensive or too complex. So you have to somehow make judgment, and in many cases to group things together. For instance, if I have a log that contains lots of GI informations, and you may have a layer of fill, and then you may have some decomposed granite, but maybe some grade 4, grade 5, grade 4, grade 5 sandwich. And then come later, you have grade 4, grade 3 rock like this. That's a little bit complex. And then you don't want to build a model like this. So you may simplify like, oh, this is fill. And then I call all these CDG. And then this is my HDG, highly decomposed granite, like this. So you group things and you assign properties, engineering parameters. For example, fill, I may do laboratory tests. I found this is C equals to 0, 5, equals to, let's say, 30. And then CDG, I may do some other structural tests and get other design parameters. Okay, so this is your ground model. Has been simplified from the geological perspective, and you know the values of those required parameters. Gamma, for example, unit weight. Okay. For example, you need to design where will be the groundwater. Okay, so that's the second model. Then if this is a slope problem, you build your design model in slope W. If this is a soil structure interaction problem, you build your model in Plexus, for example, Plexus 2D. The reasons why you have to build this design model is you want to investigate the response. Response of the ground due to what? Due to your proposed work. For example, you may want to cut away some soil. This is your proposed work. You may want to construct a building. This is your proposed work. So your ground will respond to the proposed work, and then you use a design model to reflect it, to assess it, to examine it. This is the design model. Okay, so this is a very general 3 steps approach that we often use not only for slope problem, but any geotechnical problems. Okay. Right. So in this slide, we finish at design model. Okay, so I also mentioned that likely design model, we use some softwares to help. Then you have the design model, you have to think about how we're going to do analysis. For instance, we could have the limit equilibrium method, which we talked about last week, right? We consider force equilibrium things, and we get factor of safety. This is one way of analysis. Another way of analysis is to use finite elements or finite difference. And finite elements is a technique to do approximations, same as finite difference. To me, this is a very important concept, approximations. Why? You don't expect your finite element program give you the exact solution, which means you build a model and your classmate built another model. Even though the model is the same, but if you cut it, for example, first model, you cut it into or discretize into smaller elements. And then your friend's model use much bigger elements, okay, bigger unit. Or your, okay, take this as examples, okay. The two analysis should give you different answers because neither of them, I would say neither of them is exact solutions. I always use one ways to explain the concept. Everybody knows quadratic equations, right? Ax squared plus bx plus c equals 0. How are you going to solve this one? We have closed form solutions, right? I don't need to do trial and error because I have closed form solutions. I will get the exact solutions. Okay, that means no matter you solve the equation, he solved the equation, she solved the equation, you use the same approach, you use the same closed form solution, you get identical solutions. If I have a x, let's say 5, bx 4, okay, more complicated equations, and assume that we do not have closed form solutions for that. What we want to do? Try and error, right? You can try different x value. And if you think this is a little bit complicated, you may think, if you still remember, I think high school, you have the so-called bisector method or Newton method, something like that, right? I know that this is my f x equals 0. Sorry, fx equals 0. I know this is fx equals 0, but I don't know what x is. And I just try different x value. I try this x value, I try that x value, and then I think, well, this x value give you f greater than 0. This x value give you f smaller than 0. I know the solution is somewhere in between. And then I take the midpoint. So midpoint is this one. I check this two. And then I think, oh, somewhere in between. Then I take a midpoint. And by doing this iteration process, you approach to the correct solutions. You approach. Depends on where you stop it. Right? So this is approximations. Why I have to emphasize that? Because don't be stupid in the sense that you build a finite element model, you build a plexus, and then you run the analysis, and then you give me answers like the ground. Let's say I have excavations here. I excavate this soil out. So I look at this pond. I want to know how much is settled. And then I give you the answers like the settlement, vertical settlement at this point is 2.4, 5, 6, 7, 8, 9, 10. 8, 9 cannot be 10. 8, 9, 2, 3, 4 millimeter. It doesn't make sense. You don't have the accuracy in that. This is approximations anyway. You don't need to report so many digits. They are not significant. This is a way I'm very concerned on this because it demonstrates, are you a professional engineer or you simply copy what you get from the Excel spreadsheet and then just copy a chunk of numeric values and then paste on the report. You haven't screened it by yourself. You don't actually understand what happened. Just like when you report your factor of safety, don't put down 1.4, 5, 2, 3, 4, 9, meaningless. You don't have that accuracy. They're approximations. Even you use method of slice, you cut it into 10 slices, you cut it into 20 slices, you get different solutions. Maybe up to 2 decimal places, you get the same one, and then the rest different. You use different method. You use Jambu, you use simplified Jambu, use Bishop, simplified Bishop, Morgenstern. They all give you different answer because they are all approximations. Okay. All right. So numerical approach is will give you approximate solutions, and this is also another way to do stability analysis. But numerical analysis of flag, not flag, flag the same, but plexus, be very careful because it will not give you factor of safety. It will give you stress and strain. And then you may make assumptions, for example, if the strain or if the deformation is larger than a certain value, you consider this is not acceptable. And you may even call this as a failure. Right? So you have to define. Okay? Now, that was how we do the calculation things or the approach things. Let's come back to a little bit more about Hong Kong practice. There are certain things that we still need to consider, but not from a calculation perspective, but from construction perspective, from how we detail the construction, how we detail the selections of materials. In Hong Kong, we have to consider these corrosion protections. There are different classes. So I don't go into details, but what you could understand is that according to different site conditions, groundwater acidity, for example, you have to pick different design type. Class 1, Class 2, Class 3. If this is Class 1, it is the most stringent one. Okay. If this is Class 2, better. Class 3, the most relaxed part. This is on the steel reinforcement, whether you have to do coating, galvanized coating, okay, or what standard you have to do. Let me highlight Class 2 because it will affect calculation part. If you consider this Class 2 case, even you use a, for example, maybe a let me see if I have any examples later. No. There's no examples. That's okay. I say a number, which is typical one. For example, I use steel reinforcement diameter of 32 millimeter. Okay. According to the calculations guideline for Class 2 nails, you cannot use 32 millimeter when you do the calculations. You have to do some sacrificial thickness. 2 millimeter in terms of radius, which means your diameter, instead of using 32 to do the calculation, you use 28. What's the effect? The cross-section area will be reduced. If you got a reduced cross-surface area, the axial capacity, tensile capacity will be reduced, right? Because your axial force capacity will be the tensile, allowable tensile strength times the area of the steel. Now the area of steel, instead of using 32 millimeter to do the calculations, you have to turn it into 28. So if area reduced, even though you're talking about same steel, same strength, same stiffness, everything the same tensile capacity, but the tensile force will be reduced. Okay, so that's one of the effects. Okay. Some more things on durability, and some of them has been mentioned. For example, you have to do galvanized steel. You have to provide plastic sheeting, so it's basically a cover, plastic cover, okay, enclosing the steel bar to protect it from corrosions. And definitely you also have the cement grout, just like concrete cover to protect it from corrosions. Of course, you definitely have cement grout anyway, otherwise you can't bond your nail with the soils. In the practice of Hong Kong, we also have guidelines to tell the designer what factor of safety you should adopt when you do the design. And we use the so-called consequence to life approach, which means we basically consider two things. First is consequence, or consequence to life. So what if there's a failure? What would be the consequence to life? And it's very clear. If your failure will affect some important assets like residential building, educational, so schools and bus shelter, railway platform, these kind of things, this is critical. So we call category 1. And you can actually tell because the chances of hitting people or claiming lives will be high if you got this building. Bus shelter, people there waiting for transportation, buses, railway, the same thing. Residential, everybody clear, right? Industrial, commercial, lots of people. Educational. Another important thing is think about if you got a primary school there. If you got a huge collapse of a huge slope right next to that, maybe you kill hundreds to hundreds of children. This is something that any society cannot take. So high consequence. And if on the other extreme, it will affect road, but the traffic density is low. So very likely you got a slope failure, your debris will hit on the road, but there's no transportation, no traffic there. So well, you gotta have some maybe low chance of consequence to life. So that's how we determine this consequence to life. Another way to consider the problem is economic consequence. So how much economic loss would that failure brings to? And again, everything would be pretty straightforward. If you got failure affecting country parks, maybe you think, okay, just leave it. Okay, I don't have money anyway to restore it. So the consequence, economic consequence will be low. But on the other hand, if this is a very important buildings, then you have to restore, or maybe you somehow damage the building, you have even need to demolish the building and build a new one. High consequence, economic consequence. So we got category A. And it's very clear, even I haven't moved to the next slide, you see that the factor of safety shall address both consequence to life and also economic consequence. And it's basically a matrix that consider both factor. So here comes the matrix. For new slopes that you use saw nail to do the upgrading works, this is the matrix. So you see that in the worst combinations, we have to adopt FOS 1.4. In the very minor situations, maybe just above 1 is okay. All right. Now, this is definitely a practical considerations because whatever constructions, whatever upgrading works will need financial support. So we have to consider how we're going to spend the money on. So that's the reasons why we have these considerations. It doesn't mean that if we design something, let's not put it this way. It doesn't mean if you live in different buildings, if you are different ages, you got different sort of values, human life values. No, not the case. But try to strike for a balance between the economic and the life consequence. This is for new slopes. If I got an existing slopes and I know the factor of safety is not good or not satisfactory, and I use another table. And this one, I simply consider the consequence to life if this is an existing one. Okay. All right. So this factor of safety, if you still remember, when we talk about stability, we have the external stability, we have the internal stability. This 1.4, 1.2 things are or will be applied to your slope stability FOS. How about internal failure? How about the tensile breakage of the steel bar? How about the slippage between the grout and the nail? We have another table. This is for internal failure. So you see tensile failure, we use 1.5. And then other types of failure, we use 1.5 or 2, depending on situations. Okay. Then I need to highlight this one. Why we have two different things. Both talk about soil and ground interface. Why we have two different factor of safety? You see that the key is for the first one, we talk about transient load. Second one, sustained load. So what's the difference? Let me try to use some examples to illustrate. I got a slope. Okay. I cut it. Maybe this is 45 degree. Okay, I cut it anyway. And I do the calculations. The FOS is not sufficient. The slope has been formed, right? I cut it during dry season, for example. So I got matrix sections here. And maybe soil is not that bad. The soil gets some real cohesion, for example. So all these factors, or maybe dry season, so the water table is rather low. So the slope can actually stand like this. But based on calculation from numbers perspective, the FOS is not sufficient. Maybe I need to design up to 1.4. And now the current, slip plane failure surface is maybe just 1.1. Not good enough. I design saw nails to reinforce it. With this saw nails, I could bring the safety margin back to 1.4 and above. That's good. Okay. Think about it. The slope doesn't have any problem, doesn't have any movement. It could stand. You install the nail like this, like this. No movement at all. There won't be any mobilizations of tensile forces, right? It's stable. Then maybe water table rise. Rainfall could be rise to a high level. And we all know that if you have a change in water table, your FOS will change. And in this case, if your water table rise, what happened to your FOS? What's going to happen? Drop, right? Because the slope will be less safe because the shear strength will be reduced. In that case, maybe the slope wants to move a little bit because it's approaching instability. Approaching, okay, not really unstable, approaching. Now your nail will try to help. And that's the purpose of having that nail, because the nail will try to help to stabilize it. So when the water table is high, your nail will try to help, which means during these high water table conditions or situations, you may have some little tensile force here. Okay, little tensile force. Your water table will not remain high for entire life. So it may drop back. If that's the case, it's okay, safe. So your tensile strength, your tensile forces will not be mobilized. So the nail will go back to the zero internal stress state. That's the meaning of transient load. Transient means temporary, only happen during a short period of time. So you expect your nail to take up load for a short period of time, and then nothing. And then maybe another wet season, it take up a little bit of load, and then nothing. Okay. This is what we call carrying transient load. If that's the case, we think 1.5 in terms of the soil grout interface will be good enough. Of course, this is there will be another criteria, like you must be born in a very good types of material, granite, volcanic rock. Okay, we are not talking about born in field, because field, well, we all know that is not a good sort of materials. Okay, this is transient. I want to highlight why we have transient. Second note, sustained low. Sustained low means you always have the load. No matter the water table is high or low, you always have the load. Why? That would be happening in another scenario. So now, instead of using it to stabilize a already cut slope, this is already cut, I could use it to support construction. Let's say I have a ground, level ground. I want to build a road here. Okay, I need to cut the slope. Maybe I got something here, so I cannot cut it like a very gentle slope. I have some constraints. Okay, maybe I have some structures here. So I need to cut a rather steep slope like this. Okay. And I know that the slope is so steep. If I cut it in one go and then apply nails, it cannot actually stand itself when I have the entire slope cut. When I remove all the soil, it can't stand itself. So what I do, we will have a so-called stage excavation. Let me show stage excavation. I may first excavate the first 1 meter or 1.5 meter. And then I install one row of nail. And then I excavate another maybe 2 meter. I install another row of nail. Okay, staged excavations. Excavate, install nail, excavate, install nail. And you can imagine, because this is a little bit too steep, stability is not that good. So if I keep excavating like that, when we, for example, cut in the third layer, the stability may not be very good, which means the soil may want to move. And in that case, your nail will try to help to stabilize it. So the nail will take up some forces. And you know that forces will not return to zero, because it's not due to the fluctuations of water. It's due to the constructions. And at the end of the day, you're going to take out all the soils here. So when you got a load develop here, the load will not go back to zero. This is what we call sustained load. You got load in your nail for its entire life. And we have concern. And well, the concern could be, well, drive into rather deep, but here, if I want to make life simpler, is that we want extra safety margin for this case, because we don't know what's going to happen to the nail, to the entire system, if the nail has been holding a sustained load. I give you one very simple thought, is that if your nail is holding a sustained load, you may think that the nail may, with time, it creep, it elongate, because it's holding the load anyway. What's going to happen? The nail elongate, the slope will move further, additional movement. So we worry about that. We worry that if the nail elongate, all this grout will crack, lots of things may happen. So we want to have higher FOS on the grout interface. And that's the reasons why we use tool, which provide additional safety margin. And also, if the soil is born in other types of material, so maybe born in not weather granite or volcanic, some worse sort of material, I also want to have additional factor of safety. So we use 2 instead of 1.5. That's the reasons. Okay. Now we start to have equations. First equation is simple, and you know that it's basically used to check whether the nail will, or your steel reinforcement or your reinforcement will break due to tension. So the tensile capacity of the nail depends on the yield strength of the steel, if we talk about steel, area, and remember this area you have to take into considerations of this sacrificed length, sacrificed radius. So you have to minus 4 millimeter in terms of the diameter, and then divide by a factor of safety and 1.5, right? So you know the allowable tensile capacity. And then you compare this capacity with the forces that you expect your nail to take. And you need to ensure that this capacity is larger than the force that it's going to take. Otherwise, it will break. Here, I give you some common value for the characteristic yield strength of steel that we normally use in Hong Kong. The Fy will be 500 megapascal. Okay. Think about that. Normally, when we work with soil or geotechnical engineering, we always talk in the order of kPa, strength, right? C dash kPa. We seldom touch MPa. Why? MPa is very large. And that gives you some sort of idea that this mechanism should not be controlling. Steel is so strong, should not be controlling. We still need to check, but unlikely this is controlling. And this is what I mentioned earlier. When you calculate the characteristics or effective area, you don't simply use diameter of your nail or your steel reinforcement. You have to minus something, okay? Minus 2 mm in terms of radius, which means 4 mm in terms of diameter. Another check will be on the soil grout bond. Let's take a deeper look. What happened around your reinforcement? So you got a steel. I keep calling it steel, but you know it could be non-steel, right? So you got a reinforcement, and next to the reinforcement, this is the grout that we inject into the hole, and then you got in situ soil. This is a system. This is a sandwich that happens in the ground. This equation is used to check the soil grout bond. So between the soil and the grout. Why? Because your grout reinforcement can be very perfectly bond. And then the slippage will happen here. Right? The whole grout thing will be pulled out. So we have to check this soil grout frictions. And the equations, if you take a look, it sounds like what? It sounds like your C sigma V, C dash times sigma V tangent phi. Right? Very like the Molecular thing because this is friction. Okay. And all the all other things will be pretty straightforward, right? The length, L, bond length, and then bond length, and then the parameter of the ground, because you need to have the parameters to work out the entire surface area and multiply by the C. What puzzle many engineer is why we have D, why we have 2D, why? What happened? My understanding that 2D comes from these simplifications. If you look along the nail, you expect to see something like this. You got a nail reinforcement, you got a zone of grout, you got soil, right? And you may consider like, oh, this first part is the cohesion times the PC, which is this one parameter, and length, so the bond length into the paper. So first term, pretty good. Second term, it depends on the stress level. So if your nail is 10 meter below ground, you got 10 meter of overburden acting on it. Why we need overburden? Because it is frictional. So we have sigma, V, and mu. Mu is simply tangent something, right? Maybe I use tangent A here, which is the frictional properties at the interface. Why 2D? 2D is used to describe these two planes. So they suggest that the vertical pressure is acting on this cake. You got the vertical pressure acting on this small element. And the width of this small element is D, quite close to D. And that's the reasons why you have the funny value of 2D. Because we are talking about the frictions along this plane and this plane. Okay. So this is tangent phi. Mu is actually tangent phi. And tangent phi, this phi is the frictions here. And of course, they don't use the grout. They simply use the soil one. So this theta A is actually simply theta. They use it to describe the frictions and then over a factor of safety. And you see the notes here. In most cases, this is the controlling one. This is the one that controls the length of your nail that require. This is also the one that controls how large the bar size you need to have. Not the bar size, sorry. The length of the nail, L. Controlling the bar size will be this one, but this grout reinforced interface will be this one. Is, well, at least based on my experience, is not the most controlling one. Okay, the most controlling is still the soil grout interface. Anyway, we still have equations to describe the whole thing, and this is rather mechanical, right? And indeed, GO or GeoGuide simply copy the equations from other guidelines, and you have a lot of factors here, thing, but you can actually read it. And I copy those factors because these factors depends on some, well, coefficients or some properties of concrete things, and they make reference to the British standard, and I extract that particular part. So you see eta 1 will be 1 when you consider this is good conditions. Eta 1 will become 0.7 when you consider other cases. So it's rather subjective. Okay. And different size, you have different eta 2 value. So rather mechanical. You plug in the equations and then you check. So you have to make sure that these three things, allowable tensile capacity, allowable grout reinforcement, and soil grout are all okay. In practice, one good way to do is you first assume a length, and then based on the length, you do the calculations. Based on this L, you do the calculations, and then you check whether your, take this as example, and then you check whether your, let me put it this way. You have your, let me use this one as an example. I don't want to complicate the whole thing. Later on, I use a practical examples to do. So here, give you some other values for reference. And don't worry, I won't ask you to do calculation at this for this part. Okay, so you don't need to remember all these values. It's basically look up from tables. Okay. Some more, a little bit more details here. Give you the normal bar diameters that we use in Hong Kong. You don't specify some diameter that you cannot find in the market. Okay, so most commonly we use 25, 32, or 40, and there's no point to use very large diameter reinforcement. First of all, it's too heavy for the construction worker to handle. Second of all, you don't need that. Okay. And second thing, nail length. We normally do not use so long nails. There are many problems with long nails. One very practical problem is it's very difficult to handle. You may argue saying that, oh, anyway, we cut it into segments and then we use cupola to connect it. Yes, but think about you want to insert a very long nail into the hole. It could be a problem. When you drill a very long hole, because if you don't drill a hole, you cannot put the nails in. When you drill a very long hole, you actually cannot guarantee the alignments of the hole. Maybe you design like, let's say I have a slope. This is your hole, 20 degrees, right? Normally, 20-degree hole, 20. You drill the hole like this because your drilling machine got some weight. When you drill it, it actually drops. So it's no longer always 20, especially if you got a very long nail length, right? Long hole length, you can't guarantee it shift, right? No matter horizontal or vertical. So we don't actually promote the use of very long nails. And of course, if you use very long nails, that means you got high risk of entering some adverse settings, right? You got higher chances to meet something that you don't want to encounter. For example, there may be some weak zone here, There may be some clay materials here. You don't want it. So try not to use very short, long nails if the calculations, from the calculations perspective, is okay. And the last one is we do not recommend very widely spaced nails because we also use the nail head as a cover protections, surface protections. So spacing 1.5, 2 meter is often used in Hong Kong. Details, I think you can read it yourself. It's nothing complicated, just practice in Hong Kong. Okay. I have a design procedure example. Let's take a break, and then I will illustrate as an engineer how we design a saw nail slope, step by step. Okay. Don't go into equations, but step by steps. So let's take a short break, come back 8:50. Okay, 8:50. Right, in the following few slides, I'll try to provide you what exactly a design engineers will do when we have a slope upgrading works to design. And in this case, we use saw nails to upgrade the slopes. First, very first, you still remember the three model approach, right? The geological model, the ground model, and then the design model. This is the design model. We consolidate all these informations and then we simplify. For example, in this case, we simplify the ground or simplify the problem into two-dimensional. Two-dimensional is also a simplification, right? Everything happens in three-dimensional. So two-dimensional, we have a very simple ground profile. We have CDG on top of HDG and then bedrock. We also use these vertical pressures to demonstrate, and in this case, we have some buildings here, we have some other structures here. So we have this 20 kilopascal loading. So we have the design model. Also, the groundwater, also the sea fine value. Okay. So here, the design groundwater, you see that is very conservative because we put the design groundwater table actually on the slope surface. Is basically the highest, right? You can't hide that. So we set up everything like this. And then this is a slope W platform. We sketch a number of potential failure plane. So you see we label it 1, 2, 3, 4, 5, 6 here. I make it manageable. So I pick an example that we only pick 6 slips. If you got more complicated problem, more benches, I say, you may have more. Okay, you may cut more. So once you have these everything set up, the run equilibrium, you may pick Morgenstern price method, which is a method that we often use in slope W analysis. And that will fulfill both force equilibrium and moment equilibrium. So, but that's a little bit beyond what we want to talk today. And we summarize the findings like here. We got 6 slips, and then the minimum one will be slip number 5, which is 0.8 something. Definitely not up to standard. You may get a feeling that the friction angle is 35, not too bad. You got a cohesion of 5 kilopascal, not too bad, not zero. You got a rather normal unit weight, right, for CDG. HDG is even better, 6 and 37. FOS seems a bit low. This is not very steep. Why? Something wrong? The slope looks quite gentle, right? This is 1-to-1. So it's less than 45 degrees indeed. Maybe just 30. It's not too bad, right? The friction angle, cohesions. How come the FOS is so low? Any reasons that you can think of? Very high design groundwater table, right? Very high water pressure in this case. If you still remember what we have done in the infinite slope analysis, water have a huge effect on FOS. If you got a parallel seepage, the FOS will actually reduce by 50%. So here, if this is dry, maybe the slope got a FOS of 1.4, 1.5. But because of this seepage, because of high water table, here we don't actually model seepage. This is the limitations of slope W. We simply consider the hydrostatic water pressure, but that's okay. It's on the safe side, as I mentioned last week. Anyway, we got a FOS smaller than what we need. So we have to move to stage 2, step 2. is we have to design the slope upgrading work, saw nails. What we do, we simply use equilibrium. What do you mean by equilibrium? Even here in slope W, we draw very fancy things. Actually, what you consider is I got a slope, I got a potential failure plane, I got nails, force. For example, you got a nail here, nail force, and then you got a self weight, right? And then remember we have what? You have the shear, we have normal force, like this, right? Equilibrium. So without the saw nails, you simply have this one, and then you have the shear, you have normal force, you have W. And it's not sufficient. That's why we have nail. And in order to model the nail in slope W, it all becomes forces. So we need to add forces to stabilize it. Here, I didn't sketch it like the method of slice, but the same thing actually, because these forces will apply to the slice. Okay, same thing. So if I make it a little bit more explicit, you will expect to see like I use method of slice. So this is a slope because we don't have sufficient space here. So I say, well, let's say this is the failure plane. I have method of slice, so maybe I only got 3 slices to make life simple. Then I got nail force because I will install, I use different color. Maybe. I will install nail at this part. I will install nail at this part, maybe. So it means that I would have forces here. I will have forces here. So when we consider this slice, I have one additional force. When I consider this slice, I have another additional force. Okay. So everything is still equilibrium. But we use slope W. So slope W will help us to do all these equilibrium things. Okay. And then we will know how much forces we need to make even the minimum FOS greater than 1.4. For example, in this case, we have to design 1.4, which means we will know for each row of the nail how much forces we need. For example, now here, pay attention because the unit is a little bit tricky. I know this row of nail should provide 43 should be kilonewton. I think it's a typo. Should provide 43 kilonewton per meter in order to satisfy the stability. Here, per meter, why I mean you have to be careful. This per meter doesn't mean per meter along the nail. No. Per meter is per meter into the paper because we're using two-dimensional analysis. So if you look at from the front, this is your slope. You got a nail here, you got a nail here, you got a nail here, you got a nail here. If each nail, the spacing is 1 meter, then, for example, I'm talking about same row, each nail will take 43 kilonewton. This is also 43. This is also 43. This is also 43. because every single meter I got one nail. But if I actually provide nail every 2 meters, so the spacing becomes 2 meters. Each nail should not only provide 43 kilonewton, because I got nail every 2 meters. So in this case, each nail should take 86 kilonewton. The spacing has changed. Okay. All right. So you have to be very careful when you see this per meter. This per meter is per meter into the paper, per meter into that two-dimensional analysis. Why? Because if we use 1 meter spacing, later on each nail will be taking up 43 kilonewton. So I will check everything against 43. Whether it'll be tension, whether it'll be debond, everything is on 43. But if my design is every 2 meters a nail, then my design will be against 86. Each nail would take 86 kilonewton in order to balance the whole thing. So my checking of breakage will not be 43, but 86. Okay? This many design engineers, when they first do their design calculation on slope, will make these mistakes because they will simply extract the value in your two-dimensional slope W analysis into the spreadsheet and then check all these stability, internal stability. This is incorrect. You have to consider what happened in your actual design, whether you're providing 1 meter or 1 or 2 meter. And in many cases, 1 meter is too small because you have to provide lots of nails then. So probably we use 1.5. Anyway, you know what I'm saying. Pay attention to this one. Okay, so suppose we know the forces to satisfy equilibrium, to bring it to enough or sufficient FOS. We know the arrangements of the nails, so we know what will be the forces on each nail. Then we check the 3 things. Tensile strength, check the bond strength between soil and grout, check the bond strength between grout and steel, which is this one, these equations, and these equations. Okay. That's why in slope stability analysis, when we do these calculations, is at least 2-step things. First, we use slope W, helping us to deduce how much force we need for each row. And second, we go back to that 3 equations to check whether it will break, whether the bond is sufficient or will slip. Unless all these 3 criteria are fulfilled, then the job is done. Okay? Any questions? So the second part, the first part we use slope W. The second part, normally we use spreadsheet, Excel, do calculations. And you can easily derive or prepare your own spreadsheet. But normally when you work in any company, they have their standard spreadsheet to do. Okay, any questions? Of course, when you practice as an engineer, this is not yet the end of the story. You have all these calculation things, and then you have to prepare the construction drawings. You have to prepare the construction notes, lots of things, report, lots of things. But from the calculations perspective, this is what you need to follow. Right? Questions? We discussed quite a lot of things today, even it's just on saw nails. But any questions? No. Oh, good. If in the final examinations, it's clear, not much calculations I will ask, but I haven't set up the question yet anyway, but I will ask something like maybe procedures. Okay, normally what steps you need. Maybe the, let me see, anything I could ask? Let me quickly take a look. Maybe I will ask, what's the difference between transient load and sustained load, which we spend lots of time to discuss. Maybe I will ask you about failure mode, right? What's the difference between internal, external failure mode? These kind of short questions, not much calculations, but to test your understanding. Maybe something like the working principles of saw nail, which is a question that I, even during interview, I like to ask. And then the keyword is load transfer. Okay, the keyword is you have frictions, and then you transfer the frictions to the tensile force in the nail. So we want to mobilize the tensile force of the nail to stabilize it, something like that. Okay, I've prepared. Next chapter is on loose field slope, but I think everybody's saturated today. So let's make it next week. Okay. So remember your assignment number 1. If you don't submit it, nothing I could do to help, right? Don't expect that I can extend the deadline. No, I won't extend the deadline. Okay, so let's stop here today.